Section 4.3, we're going to still talk about the fundamental theorem of calculus. Now, I already introduced you to part 2 of this theorem. We're going to take a look at part 1. And it ties back into graphing and seeing the area under a curve. So go ahead and pause the video and just copy this down for right now. So this curve right here is just y equals f of t. Now notice I sort of stopped this from a to x. I'm going to shade in the area right here just from a to x. And I'm going to call this its own function here. So I'm going to let the area be represented by the function g of x. So g depends only on x. And we're going to call this the area so far function. It's the area we have so far, but we're going to turn it in, call it a function. So g of x is the area that we have so far, and we're referring to it as a function. So this is the fundamental theorem of calculus part 1. So since area can be written as an integral, we're going to let g of x be the integral from a to x of f of t dt. And we always talk about f needs to be a continuous function on this closed interval from a to b. X varies between a to b. Now g is also continuous on the interval, closed interval from a to b, and differentiable on the open interval from a to b. So what this means, this is a huge part, and I'm going to illustrate it a little bit later in the video, that if we took the derivative of g of x, it just turns into f of x. So our first example, we're just going to look at sort of like just area under a curve so far without perhaps knowing the actual values, but starting to look at this in terms of this statement that's right here. So pause the video, please go ahead and copy this graph. So f is the function whose graph is below. This is just y equals f of t. Now, as you're copying this down, let's sort of break this up here. So I'm going to stop this in sections. Now we're given here, again, g of x is equal to the integral from 0 to x of f of t dt. And I'm also giving you this statement right here. So in a way, we're going to use properties of the definite integral. But it's our job to find g of 0, g of 1, all the way up to and including g of 5. Now, what we're going to do is substitute all these values back into here. So now, if g of x is equal to the integral from 0 to x, g of 0, notice this is g of x, so x becomes 0, is equal to the integral from 0 to 0 of f of t dt. And we saw this from our properties from section 4.2, because these two are the same values. Guess what? That equals 0. Next, we're going to find g of 1. So g of 1 is the integral from 0 to 1 of f of t dt. Well, according to the graph, since we don't actually have a function, we use area. So if you notice, because I have a line segment here, this creates a nice triangle. So to figure out this integral, I'm just going to use the area of the triangle that's shaded here. So that's going to become 1/2. Our base of the triangle is 1, and our height is 2. So this integral is equal to 1. Next, we're going to take a look at g of 2. So that's equal to the integral from 0 to 2 of f of t dt. So now this is going to be the area from 0 to 2. Well, if you notice, I already found the area of what's in blue. So let me just kind of go back. So if I just now shade the area between 1 and 2, that's another nice shape, a rectangle. So all I have to really do is add this 1, because that was what was in blue. Let me actually put that in that color. So I already found the area from 0 to 1. And now I'm going to add the area of the rectangle. So my base is 1, my height is 2, so that's going to be 2. So this will equal 3. All right, next we're going to find g of 3. So that's going to be the integral from 0 to 3 of f of t dt. So I don't have a nice geometric shape here, but I can separate this and say, well, this is using the properties. This is equal to the integral from 0 to 2 of f of t dt plus the integral from 2 to 3 of f of t dt. So we already found the 0 to 2 part. That's over here. So that's 3. So this part here is equal to 3. Plus, now the 2 to 3, that's what's given right up here. That's equal to 1.3. So we add those together, we're going to get a 4.3. All right, now let's find g of 4. Again, g of 4 we can say is the integral from 0 to 4 of f of t dt. But then we can also use the properties to separate this because we just found 0 to 3 of f of t dt plus 3 to 4 of f of t dt. So how can we figure this out? So the way this is intended to be drawn is that this area right here is the same size as this area right here. But because this is underneath, so this area right here, that was the 1.3. So that means this part right here is going to just be a negative 1.3. So if we had the area from 0 to 3 was a total of 4.3, and then this was a negative 1.3. So it was like we added all this area together here, but now we start to take away from it. So we were taking away from it exactly what this equals. So now we're back down to 3. And now g of 5. So we could just go ahead and say it's the integral from 0 to 4 of f of t dt plus the integral from 4 to 5 of f of t dt. And again, this was intended to be the same as what's over here. It's symmetric. So this area 3 is actually going to equal this area over here. So this is another negative 1.3. So the integral from 0 to 4 of f of t dt was 3, and then we're going to subtract another 1.3 from it, or add a negative 1.3. So we actually get 1.7. So I hope that was a little easier to follow. So exactly what I was just kind of referring to here, talking about area. Since f of t is above the x-axis, it's greater than 0 for all values t less than 3. So everywhere here, this area would turn out to be a positive number. We keep adding area. So we added area, the blue, the red, and the purple. We added all of those together. So g is increasing up to t equals 3, where it attains a max value. Now for all the values of t greater than 3, g starts to decrease. We saw that because we got up to a 4.3, but as soon as we went between 3 and 4, we started to take away from the area because that area was below the x-axis, because f of t is negative there. So pause the video to continue writing that down, but it's a very important way to look at this graph. Sometimes our questions might be phrased that way. All right, what we're going to take a look at now is if we were to take the derivative of the antiderivative. So this is also part of this fundamental theorem of calculus. So what's here in purple is really telling us we're taking the derivative of the antiderivative. Well, these are actually inverse operations. So you would think things would cancel out, and they do, but they cancel out in a very unique way. So the derivative of the antiderivative of f of t, you would think everything would just cancel and we would be left with f of t, but we're not. We're actually just left with f of x, and it has everything to do with what's up here. So I'm going to take you through an actual example which will make this make sense. But again, a couple conditions here. F is continuous, and that bottom value here, a, has to be a constant. So we are going to look at the function f of t is t squared, and then we're going to find the derivative of the antiderivative right here. So please go ahead and copy this down. All right, so we are going to find g prime of x. So let's start with this first, though. Let's say g of x is equal to the integral from a to x of t squared. So instead of f of t, I'm actually going to put the t squared in here, dt. So let's go ahead and evaluate this or figure this out. So the antiderivative of t squared would become a t cubed over 3, and I'm going to evaluate this from a to x. So what this means first is I substitute the x in, so I'm going to get an x cubed over 3 minus this lower value in here, a cubed over 3. So this is g of x. So now if I wanted to find g prime of x, I'm going to take the derivative here. So notice I no longer have t's up here. I have the x, and then a is a constant, remember. So if I took the derivative of this first term, I'm going to get 3 times x squared over 3. And then the derivative, remember this is what I just said, a constant. So the derivative of a constant is 0. So now this just turns in to x squared, which if I go back up here, if f of t is t squared, f of x is x squared. So then that just turns out to be f of x. So going back up here, the derivative of the antiderivative turns out to be f of x, and that has everything to do with what's right up here. So the shortcut was, yes, stuff canceled. We were just left with f of, not necessarily t, we were left with f of x because we had to evaluate that. We had to substitute that x in. So let's take a look at this example. We want to find the derivative of the function g of x here. So using that statement, g prime of x, again, you would think everything would cancel here, and it does. We're left with the square root of 1, not plus a t squared, but plus the x squared, again, because that's what we're looking at. Notice down here, that's a 0, that's a constant. Now this next one is a little bit more challenging. All right, so you would think the same thing would happen here, that if we just looked for y prime, it would just become the square root of tangent x plus the square root of tangent x all underneath, and it's close. But because this isn't just an x up here, it's another function, we have to do a little bit of work off to the side. And eventually we're going to get into something called u substitution. So we're going to let u equal to tangent x. I'm going to just call it a different variable. But now we have to actually take the derivative of this. So then du with respect to x, du over dx, the derivative of tangent x is going to be secant square x. Now what I'm looking for is y prime, which is dy over dx. So I need to rewrite, I need to connect these pieces. So dy over dx is actually going to equal this is just a manipulation, dy over du times du over dx. So I divided by a du, then I multiplied by a du, but that's what this is right here. So dy over dx, which is the integral from 0 to tangent x, actually put the d in front of it, so because that's the y. So I'm going to have d over dx times the integral 0 to tangent x of the square root of t plus the square root of t dt. So this right here, this is my d, this whole expression here is my y over dx. So to translate this now, this is going to equal dy over du. So here I'm putting d over du. Now my y is 0, but in terms of u is now tangent x of the square root of t plus radical t dt times my du over dx, which is secant square x. Just to separate that. I know this looks a little strange, but this right here, this is all my dy over dx is equal to du over dx times, I'm sorry, dy over du times my du over dx, which is secant square x. So now what I could do with this part is use that shortcut. So this becomes just the square root of whatever's up here, now that I have that down to a single variable. So u plus the square root of u times secant square x. Now, again, u is tangent x, so I am getting the square root of tangent x plus the square root of tangent x times secant square x. So it kind of has a little similarity and familiarity with the chain rules. So we followed this, but then we also needed to multiply it by the derivative of the inside stuff that's there. But that's it. Like I said, it's a little bit more challenging than just following the last two examples. All right, the rest of this section ties in nicely with what we were already doing in 4.2, so it's just a nice review, some extra practice problems of evaluating the definite integral. So what I would suggest, pause the video, go through each problem, see what you're getting, and then resume playing to see my explanation and work for each of these. So pause the video, copy down, and try number 1. Okay, so hopefully you were able to work through this. If not, please continue to pause the video. All right, so the antiderivative of 5 would become a 5t. Then we would get a minus 3t to the 4th over 4, and then plus a 4t cubed over 3. Now you could put the vertical line or you could put brackets. It's kind of nice to see brackets around the whole thing, and then we're just going from 1 to 4. So just be very careful watching your fractions, your signs. So we're going to get a 5 times 4 minus 3 times 4 to the 4th over 4. We are going to get into some large numbers here. Plus 4 times 4 cubed over 3. Then we have to subtract all this when a 1's going in here. So 5 times 1 is just 5. Minus this will just give us a 3/4, and then plus a 4/3. So here we're going to get 20. And I see a mistake right here. I don't know. I think I was just thinking of the 3. But that should be a 3t squared over 2. The downside of making these video lessons, I don't have students in front of me to point out when I make a mistake. Luckily, I caught that, though, in that step. All right, so we're going to get a 20. Now, we could say 4 squared is 16 over 2 is 8, so we're going to get a minus 24. Now, this is really 4 to the 4th. 4 times 4 cubed is 4 to the 4th. That is 256 over 3. And then we could write this out as a minus 5, and then I'll change that too. There should be a 3/2. And then this will become a plus 3/2 and then minus a 4/3. So we can go ahead and combine as much as we can right now. We're going to have a -4 minus a 5, which will give us a -9. And then right here we could say plus 252 over 3. And then plus a 3/2. And we can go ahead and get everything over. Let's first get this over a 3 right now. So we're going to get -27/3 plus 252 over 3. And then we can still say plus our 3/2. So we're going to get 225 over 3, which is a little bit easier to work with, and then plus 3/2. Because now we can get everything over a 6, which I'm just doubling this number. So I'm going to get 450 over 6, and then plus 9/6. So we get 459 over 6. You could leave it like that, but this does simplify into 153 over 2. So understandably, we are going to work with a lot of fractions. Try your best not to use a calculator, but if you need to, you can. As I've mentioned any time before, any problem like this on a test or a quiz or a writing assignment, you will be able to do quite easily without a calculator. But if you see these on WebAssign, you could use a calculator, but just know how they want the answer. If they still want it as a fraction, make sure you're doing that and not letting your calculator turn it into a decimal. All right, go ahead and pause the video again and try number 2. I'll give you a hint. Rewrite radical x as x to an exponent, a power. All right, so this could be helpful of showing the integral from 4 to 16 of x to the 1/2 dx. So now the antiderivative, we're going to get x to the 3/2 over 3/2 as we evaluate this from 4 to 16. So I do want to simplify this. This is going to become 2/3 x to the 3/2 from 4 to 16. Now remember, x to the 3/2 is the same as the square root of x cubed, or we could write it this way. So we're going to get 2/3 times the square root of 16, we can write it this way, cubed, minus 2/3 times the square root of 4 cubed. So this becomes 2/3, square root of 16 is 4, 4 cubed is 64. And we're going to get 2/3, square root of 4 is 2, 2 cubed will give us 8. So we're going to get 128 over 3 minus 16 over 3, and we get 112 over 3. All right, let's throw in some trig functions here. So this is the integral from 0 to pi over 4 of secant theta, tangent theta, d theta. So if it helps, we could keep parentheses around that. Give this a try. Think the antiderivative. So go back and think of what you would take a derivative of to maybe get this. All right, so let's take a look. If you went back through your notes, your list, if you take the derivative of secant x, you get secant x tangent x. So the antiderivative here is just going to become secant theta, and we're going to evaluate this from 0 to pi over 4. All right, so this means we get secant of pi over 4 minus secant of 0. Well, secant is a little tricky to work with, so let's bring back in some reciprocal identities. So secant is the reciprocal of cosine. So if we just think of cosine of pi over 4, that should give us radical 2 over 2. So secant of pi over 4 is going to be the reciprocal of 2 over radical 2. Now to work with this, let's go ahead and rationalize it. Most of the times we don't, but we have to do a little bit more with it. So let's go ahead and do this. I want to multiply top and bottom by radical 2 over radical 2. So I'm going to get 2 radical 2 over 2, which is just radical 2. So secant of pi over 4 is radical 2. Now cosine of 0 is 1. So secant of 0 is a reciprocal, which is also 1. So then we get radical 2 minus 1, and we're going to leave it like that because radical 2 is irrational. Okay, just a couple more. Go ahead and take a look at this one. If you want to pause the video, I'm going to give you a hint though. There's no product rule with integrals here or antiderivatives. So a hint would be just to go ahead and multiply all of this together. So pause the video, give that a try, and let's see what you're coming up with. All right, so this becomes the integral from 0 to 2. We're going to get a 2y squared. Outside is y, inside is a negative 2y, so we're going to get a minus y and then a minus 1, and then dy. So now we can just go through and take the antiderivative of everything. So we're going to first get a 2 times y cubed over 3 minus a y squared over 2 minus a y, as y goes from 0 to 2 here. All right, so first substituting in a 2, we're going to get 2 times 2 cubed is 8, so we're going to get 16 thirds. This will give us 4 over 2, so minus 2, and then another minus 2. And then technically, and when we substitute a 0 in here, all of those would just give us 0. So we get 16 thirds minus 4. This becomes 16 thirds minus 12 thirds, so we get 4 thirds. Go ahead and copy down number 5. Again, there's another little trick to this, because we don't have a quotient rule for antiderivatives. So what I want to do is separate this fraction, and I'm actually going to use exponents here. So this becomes x to the 1/2. I'm going to put that over x squared, minus 1 over x squared. So I just separated the fraction. I can divide everything in the numerator by that denominator, and we'll keep dx. Then we can simplify this. So we get the integral from 1 to 9. We're going to subtract the exponents here, but I'm going to leave this up top because I want to be able to use that power rule. So 1/2 minus 2 is going to give us a negative 3/2. And then minus x to the negative 2nd. Now we can apply the power rule. So here we're going to get x to the negative 3/2 plus 2/2 will give us a negative 1/2 over negative 1/2. Minus x to the, if we add 1 here, negative 1 over negative 1. And this will go from 1 to 9. So let's clean this up. We're going to multiply by the reciprocal here. So this becomes negative 2. And then to be able to evaluate this, I'm actually going to flip that back down. So this becomes over the square root of x. And then this will become a minus a negative 1 here. We're actually going to get a plus 1 over x. As, again, we'll substitute in the 9 and the 1. So as we substitute in the 9, this becomes negative 2 over the square root of 9 plus 1/9 minus, and we have to subtract this whole thing, negative 2 over the square root of 1 is 1, and then just plus 1. So we're going to get negative 2 thirds plus 1/9. This will become a negative 2 plus 1 is a negative 1, so minus the negative 1 will become a plus 1. And we can get common denominators. This will become a negative 6/9 plus the 1/9 plus 9/9, and we're going to get 4/9 when we combine those. All right, let's go ahead and just try one more, and this will wrap up this section. So here's the integral from 0 to pi over 4 of 4 secant squared t dt. So using the property, we could put the 4 on the outside. Again, 0 to pi over 4, this becomes secant squared t dt. So because it's a trig function, we have to go back. Is there a trig function out there when we take the derivative of it, we get secant squared t? So hopefully you guys were able to think of tangent, right? The derivative of tangent x or tangent t would become secant squared t. So this just becomes 4 times tangent t Now, we could leave this here, or technically we could just leave it out in front as we evaluate this. So we could say 4 times tangent of pi over 4, tangent of pi over 4 minus tangent of 0. Because that's just one number, I don't really need to keep it in its own set of parentheses. So if you think of tangent of pi over 4 is right in the middle of the quadrant. So the ordered pair we're looking at is radical 2 over 2 for both sine and cosine. So if I divide that, I just get a 1. And tangent of 0, the ordered pair at 0 degrees, or 0 radians rather, is 1, 0. So sine divided by cosine would just be 0. And then we just get a 4 here. All right, so just some further examples, extra examples of evaluating definite integrals. In section 4.4, we look at indefinite integrals. So that will be the same process here, but we're not going to have values for the limits of integration.